Hi, my name is Tim Peterson. In this presentation, I'm going to be talking about a recently published paper in Science titled Watersheds May Not Recover from Drought, or here I've given it the Australian word of catchments. So this paper was published in Science, as I mentioned, early 2021, and it's titled Watersheds May Not Recover from Drought. It's received quite a bit of coverage, both in Science, where a perspective piece was written by others talking about the significance of the work globally, but also in about 100 and so media outlets around the world. So ABC did an extended story on it, as well as various US outlets along with the BBC. So here I just want to dig in a bit more what the paper's about. Before we do that, I want to talk about, what's the state of knowledge about catchments recovering from drought? And there's two broad perspectives on this that have been published before. So one is a very common one that's embedded in lots of our hydrological models, somewhat implicitly I'd argue, is well summarised by Anna van Loon. And here she shows that, we may have a meteorological drought, over some period, and unsurprisingly, surface water goes down from some average. Eventually, groundwater goes down from some average. But when the meteorological drought ends, after some time, the hydrological drought also ends, and eventually, the groundwater and stream flow come back to where they were. It's just a matter of time. Now, I've done a bit of work before that is skeptical of this, really, and it tries to bring together the ideas from ecosystem resilience to examine, what would happen if there's positive feedbacks in how catchments behave? So positive feedback being like an amplifying process. And in one of the papers in the series, I've just sort of demonstrated that here, where we may have some hydrological state variable like stream flow, bouncing around as we can see here. And then a drought comes along. Unsurprisingly, this hydrological state variable declines. But if there's a positive feedback, we've been able to show with a range of deterministic models that the catchment can potentially persist within this state. So that all sounds nice, and theoretical work showed that this is plausible under daily rainfall conditions. However, we wanted to see, the motivation for the science paper was to see, is that really what happens in nature? Is there empirical evidence for it? So to do that, we started using what's referred to as the Millennium drought as a natural experiment. I want to illustrate that here. So here is the rainfall deciles for the state of Victoria in southeastern Australia for 4 years, from 91 to 94, and then another 4 years from 95 to 98. And with white being that's within the 4th, 5th, 6th or 7th deciles, we can see that, in the first 4 years, there was probably slightly above average rainfall. In the next 4 years, it was pretty average over the whole period. Well, this is about the time when, late 90s is about when the Millennium drought started. So let's look at that. So in the first 4 years of the drought, we can see, rainfall was dry over the whole area. So rainfall was below average over the whole area. But in the last 4 years of the drought, the rainfall was severe. It was lowest on record. This drought extended for at least 10 years, depending on where you say it starts. So we had this pretty average conditions before. Prolonged drought was particularly severe at the end. And then in the years afterwards, we had a few very wet years, where we can see that there was periods in northern Victoria that were the highest on record, but much of the state was above average. And then in the last few years, it's been average to slightly below. So we wanted to use this data to understand, how can catchments actually recover? How do they really behave to prolonged severe disturbances like a drought? So the first thing we discovered that there were three key ways that catchments appear to behave. So first off, we've got the Wanangata River up in sort of the alpine area of Victoria. And what I've got plotted here is the annual area weighted rainfall for the catchment versus the Box-Cox transformed annual stream flow. And I've categorised all of these observed data points by whether they were before the Millennium Drought, during the Millennium Drought, or after the drought. And then for each of these 3 periods, fitted a regression line, sort of similar to what Margarita Saft has done a few years before. And for this period, we can see that, well, the amount of rainfall, 1,000 millimetres of rain before, during, or after the drought, produced roughly the same amount of stream flow. So that's catchments behaved as we thought. Example. Now the Yea River in central Victoria shows something different. This shows, again, we've got the 3 categories, and all 3 lines have the same slope. They're only different in their intercept. This time, 1,000 millimetres before or after the drought produced the same amount of rainfall. Well, during the drought, the same amount of rainfall produced less stream flow. So this is sort of analogous to what Margarita's shown for large parts of southeastern Australia, that there seems to be this shift going on during the droughts. But one very interesting one is Cairn River out on the far east of Victoria. This is a very remote area with lots of native vegetation. And this time we can see that during the drought, before the drought, there was this high, 1,000 millimetres of rainfall would produce high amount of runoff. Drought comes along, the lines shift down, and the drought ends, and we are continuing to have this this deficit where the same amount of rainfall is producing less stream flow. So effectively, like 100 millimetres of rainfall in 1990 before the drought is producing less stream flow than 100 millimetres many years after the drought. So we want to dig into this a bit more, though. We want to understand, well, we want to understand this apparent shift in catchment behaviour without having to assume when the meteorological and hydrological droughts started and ended. And we did that using hidden Markov modelling package that we developed. And for those that are new to hidden Markov modelling, I want to try to illustrate it. It's saying, for example, that, well, we don't know what state, a natural system is, like a catchment. All we know is what we see about that state, the rainfall and stream flow. But the state that caused that rainfall or stream flow is hidden from us. And in this little example I've just illustrated, there could be 3 potential states. There could be a normal runoff state, and each year there's some probability of staying in that state, Pn. There's 1 minus that probability of shifting out of that state, and in this case I've said we shift to a very low runoff state. And then there's some probability of staying in that state, and 1 minus that probability of shifting into a low runoff state, let's say like a recovery, and back. And over time, we never know what state the catchment is in, we're just trying to infer it from the observed data. Effectively seeing, can accounting for these shifts and the probabilities of shifting better explain the observed data. So using this approach, we simulated the mean stream flow, Q hat, at some point Ti, and at some Markov state I, as some multiplier of the annual rainfall times an auto up to 3 autocorrelation terms of previous year, the year before that, and the year before that, where these can potentially change with state. Then, most importantly, we allowed the state to differ, like that y-intercept in the scatter plot before. It could shift up and down, whether it was in a high runoff state or a low runoff state. So that's what this beta term allows for, that shifting of the line up and down with the states. And also each state has its own error or uncertainty. We looked at a range of different ways of characterizing this error and ended up settling on a truncated Gaussian and a 2-parameter gamma distribution, so that the flows were always greater than 0. We explored 68 different model combinations of these, and then for each one of those we implemented a fairly robust global calibration scheme using some constraints to minimize flickering back and forth between the states, and then calibrated each model at least 10 to 20 times. The paper goes into a bit of detail on this. Then we used what's called the Akiki information criteria to find the best model at each streamflow gauge that best explains the data with as fewer parameters as possible. We then identified what state the catchment was most likely in over time using the Viterbi algorithm, and all of this is written up in a sort of using formal object-oriented code in R and is open source. So I want to show you what the results look like. We have, here is the Wanangata River again, and then we've ran the Markov analysis, and I've got the Millennium Drought shown with the start being a bit greyed out because we're a bit unsure where it really started. And this is saying for the Wanangata River that, well, only one state was observed, the normal state, and we can see the observed streamflow in the grey line. The median flow is the circle, and then the bars are the 5th and 95th range in that uncertainty. And for the Wanangata River, only one state was observed. However, for the Yea River, we see that 2 states were observed, and that the catchment shifted to a low runoff state in 2001. It stayed in this state, it's water years by the way, and it stayed in this state until 2010, which was a very wet year when in the drought breaking. So, but in the years afterwards, the catchment seems to have clearly recovered. So, let's look at the Cairn River. Here we can see the Cairn River. The catchment shifted a little bit earlier in 1999 and has continued to stay in this low runoff state both during and after the drought. And importantly, in both for the Yea and Cairn River, I've shown here these open circles. This is showing our estimate of what the median stream flow would have been if the catchment had not changed state. And hence we can see that these wet years, this wet year after the drought, would have been even wetter, or the floods potentially greater if the catchment had not changed state. So that's what the hidden Markov modelling results look like over time. I want to show you what they look like over space. So here's the 161 gauged, unregulated catchments that we looked at that really don't have any substantial upstream storages like dams. And for 1990, we defined that as our normal streamflow years. So every catchment was in a normal runoff state then. I'm just going to jump through the years a bit. So 1995, a couple are in a high runoff state and a couple in low. The hashing texture, by the way, just means that we had to infer that year. 2000, which is generally thought of as very early on in the drought, a good fraction of catchments had already changed state. 2005, some have even shifted into this very low runoff state, in this dark red. Jump to the last year of the Millennium Drought, and we can see the vast majority of the state appears to be in a low runoff state, and the only areas that are not is this sort of alpine area out on the east. We can also see there's quite a bit of patchiness. So down in the south, for example, you can see that there's catchments of normal, low and very low right next to each other. I think this illustrates that while there may be regional climate patterns at play, there's also pretty strong local catchment processes, and I think this makes it quite difficult to predict what an individual catchment is going to, or how it's going to behave. Okay, Millennium Drought's broken. Quite a few have recovered. I'll just shift back and forth so you can see that a bit clearer. So look out in the east. You can see a few have recovered. Sorry, out in the west, I mean. But a good number of them are still behaving like they're in a drought. Jump to the last year of analysis, which was water year starting in March 2016, and we can see a good fraction of catchments are still in a low or very low runoff state. And again, we get that sort of complex sort of patchiness. So hopefully that's given you a good idea of what it looks like over space. Here I'm just showing you the change over time. So this is, if we're looking at the red solid line, this is a number of catchments in a low or very low runoff state using the annual analysis. What I want to particularly highlight is we can see that the number of catchments in this low runoff state steadily increased to about 2/3 at the end of the drought. A good number recovered straight away at the end of the meteorological drought, but afterwards we can see a good number of them are still persisting in this low runoff state. It's not like this is slowly decaying over time. This trend is not statistically significant in that it does not have a statistically significant trend. So the catchments that we reasoned from this appear to be sort of persisting in this low runoff state. We did the same in all of this. We repeated it all using some seasonal models to understand, well, maybe this is just explained by, the timing of rainfall. And that had a very similar pattern. And again, after the drought, catchments appear to be persisting in this low runoff state. Okay, but reasonable enough. Maybe just recovery is just a matter of time. Maybe eventually the catchments will recover. We wanted to examine this in a bit of detail. And here I've got is the probability for Cairn River at the top and Bem River in the south, or the bottom. I've got the probability of being in a normal runoff state over time in the green, and being in a low runoff state over time in the orange. And what we wanted to look at was, well, are maybe the probabilities of being in a low runoff state are just declining, sort of slowly getting towards recovering. So what we looked at is the slope of these probabilities over the last 3 years. We did that for catchments that had not recovered. We looked at the last 3 years of analysis. And for those catchments that have recovered, we looked at the 3 years just before recovery. And for this Bem River, we can see that the conditional probabilities were actually declining just before the catchment actually did recover. So we can sort of argue that Bem River was giving us some clues that the recovery was about to happen. We looked at this across all of the catchments that had not recovered. And here I've just got the cumulative probability of those slopes. And if we're looking at the solid red line, we can see that only about well less than 20% of the catchments showed any sort of early warning of recovering. So about 80% of them showed no evidence of recovering soon. However, the blue catchments, the catchments that had recovered, the vast majority of those did give us some warning that they're about to recover. So we argued that the catchments that have not recovered are appearing stuck there. They're giving us no warning that they're about to recover. Okay, but how much water is missing? This was actually quite difficult because we're trying to estimate what the stream flow would have been if the catchments hadn't changed state. And we've expressed this as a percentage of what the normal runoff would have been. And we can see that for large areas of central and western Victoria, the runoff that did occur was 50-ish% or a lot lower of the normal flow that should have occurred if the catchment had been in its normal runoff state. This extends in a fairly patchy way in the north and similarly patchy way out on the east, but still many areas that have you can see the variability yourself. 20, 40, 60% of the flow that would have been expected. So where's this missing? We've got this rainfall that's not making it to the stream flow. Where's it going? We looked carefully about whether it's explained by stream flow gauge or land cover change, and neither of those possibilities explained our data. So there's only a few options. It could be going into transpiration or evaporation. We know it's not going to run off. The other option is going into soil moisture storage or recharge. However, we looked at many long-term groundwater observation bores in catchments that have and have not recovered. And for the vast majority of those catchments that had not recovered, the groundwater level declined. Here I've got depth below natural surface, so the depth of the water table. It declined during the drought. But importantly, in the years after the drought, it's continued to decline. And then, at least in this case, stay flat. For this other bore, when the drought ended, we saw this modest rise, but the groundwater level has continued to come back quickly. So we argued that if this rainfall that's not making it to the stream was instead going to groundwater, we'd be getting all this extra recharge, and hence the groundwater level should be going up, not flat or continuing to decline. So we argue groundwater does not explain. It does not tell us where this water is going. One of the interesting things is others have observed that the leaf area index didn't decline during the Millennium drought. From this nice paper by Sawada, we can see that rainfall had a statistically significant trend throughout much of Victoria. Victoria roughly like that. LAI had a trend, but when we look at what's statistically significant, we can see that actually, LAI had areas that went up and down in different parts of the state, but when we look at to see what's statistically significant, no region had statistically significant changes in LAI. So the plants seem to be just as green, or just as much leaf area, before, during, and after the drought. So we argued, has the disturbance changed things? Is this missing water going to increase evapotranspiration per unit of precipitation? So we went back and looked at a really nice paper by Peterson from 2009 in Hydrological Processes. And what he did, he proposed this Horton's index, where Horton's index was the actual ET, estimated from catchment water balance, divided by catchment wetting, or how much water actually infiltrated. Simply calculated from annual precipitation minus annual stream flow, divided by annual precipitation minus annual storm runoff, which was just estimated using a base flow filter, in this case Linholic. And when we apply Horton's index, it's showing, here's a map at each of the sites during the drought, and it's showing us that, in the vast majority of the state, so centre and west, and more than 95% of the infiltrated water is being transpired. Only in the sort of alpine areas does this number drop substantially to 80-ish%. And many of these areas, as shown by the hashing, were statistically significant. Okay, but that's not really what we want to understand. We want to understand, how has this changed? compared to before the drought. So here, in Horton's index, so on the left we've got the Horton's index during the drought minus the Horton's index, or mean Horton's index before the drought. And what's interesting, we argue, is that for the vast majority, or for all of the state, almost all of the state, the Horton's index was greater during the drought than before the drought. So the vegetation was somehow able to transpire a greater fraction of rainfall. And we think these are reasonably robust given the length of observations that we're averaging. It's in the order of 7-ish years, and others have shown this should be acceptable for low errors. More interestingly, when we look at the post-drought average Horton's index minus the pre-drought, we can see that a large fraction of the catchments that had not recovered had a Horton's index greater than before the drought. So the drought came along, plants seemed to be able to transpire more water, drought ended, and plants seem to be able to continue this behaviour at many sites. Okay, so I want to try to wrap this up together and bring it back to some of the earlier theoretical work I mentioned. This is roughly what I would say is happening. We might have a period of average rainfall, and we can think about a hydrological variable like groundwater or stream flow. Initially it might be high, drought comes along, and unsurprisingly, groundwater level or stream flow decline. We return to average rainfall conditions, and I'd argue that almost all of our hydrological models, because they don't have positive feedbacks, will show that, or do show that the hydrological state variable comes back to where it was before. So we've implicitly assumed that our catchments are infinitely resilient. However, when we have a positive feedback, we can persist in this different regime as a result of the drought disturbance. And this is exemplified by a couple of the results that I showed earlier. Where I think it was for the Cairn River, we can see that it did change state, but the drought ended and it came back. However, for the Cairn River, the disturbance happened, drought ended, and we've persisted in this new and different state. So I hope you found this useful and interesting. From this, I think we can conclude that there's complex patterns of drought response and recovery. It's very hard to predict. There seems to be an interaction between regional climate patterns and local catchment processes. And I think this makes it quite difficult, what's going to happen in a particular area. I think we've shown empirical evidence that catchments can have a finite resilience to meteorological droughts. So effectively, what this means is that hydrological droughts can persist long after the meteorological drought. Big question is, well, what makes them recover? If we go back to some of the earlier theory, I think that suggests that wet years will be required for the catchment to recover, to effectively push it past the threshold and to enable it to recover. The multiple lines of evidence, we think, support the conclusion that this missing rainfall that's not getting to stream flow is likely going to increase evapotranspiration per millimetre of rain that infiltrated. So the plants are able to somehow hold on and suck up. And this might be related to the thickness of the vadose zone, but the plants are able to hold on and transpire more water. Some of the mechanisms for this and the thresholds for recovery are future work, so if you're looking to do a PhD, I'd love to have a chat. And in closing, I'd just like to quote Flavia Toro in her science article commenting on my work. It says, Peterson et al. Challenges the comforting assumption that water systems naturally tend to absorb disturbances. This emphasises a necessity to change the way global water processes are conceptualised. So I hope you found this interesting. This work could have only been made possible because of the Victorian Water and Climate Initiative from the Victorian Government. More details there on the link, and there's some tools, open source tools that have already been available. And please follow me on Twitter if you want to stay up to date with some of this work. Bye-bye.